vector has both a magnitude and a direction. If we think of the x, the y, and the z-axes here, then this vector might be r. We normally denote a vector with an arrow over the top, and that implies this vector right here. And this r implies that it has three parts. It has a part that is what we call a component in the x direction, projection here, called the x component, projection here called the y component, and a projection over here called the z component. And so often we will write a vector r as being these three components, x, y, and z, which are simply three numbers. It might be a vector something like 2, 3, 1. And that would give us our x coordinate, our y coordinate, and z coordinate. And therefore, we would say that this is equal, that x is equal to 2, y is equal to 3, and z is equal to 1. Sometimes we may denote a vector like a and call these three components a in the x direction, a in the y direction, a in the z direction, and thus put what we call a suffix on the bottom of a vector. And sometimes, rather than using x, y, and z, we might use 1, 2, and 3. So we might call this a1, a2, and a3. These are just different notations for the same thing. And whether we call it x, y, and z, or ax, ay, and az, or a1, a2, and a3, it still means that these are the three projections of this vector along the three different axes. Now generally in high school or earlier grades we learn about vectors, and we learn that we can do two operations. First of all, we can take a vector a and we can add a vector b to it. So we can form a vector a plus b, which is equal to a new vector c. Now how do we find that? Well, in the early versions we construct a parallelogram so that we put the vector b over here, or we can put the vector a up here. And you can see that this forms a parallel construction, parallelogram, such that the vector that goes from the beginning to the very end is the vector c. Well, an easier way to think of that is to think, when I add two vectors, I just put the second one at the end of the first one. And if I have several of them, I put the first at the end of the second at the end of the first, the third the end of the second, and so forth like that. So for example, if I have multiple vectors, like a, I'm going to add a vector b, then add a vector c to that, then add a vector d to that, and a vector e to that, then the final vector would be the vector that goes from here to here. This vector here would be the vector a plus b plus c plus d plus e. And I can add all of those together. So that is a very good way in 2 dimensions, at least on paper, with two-dimensional vectors to visualize them, simply as arrows that are lying there on the page. Now, if I have a vector that is the negative of another vector, it simply goes in the opposite direction. For example, the vector minus b in this diagram would go in this direction. And I can talk about a vector a minus b. That's the vector a. So this is the vector here, a. I've added the vector a to the vector minus b. I could think of it as putting minus b at the end of this one or making the parallelogram. So a minus b would be this vector here, whereas a plus b would be this vector here. So in other words, to subtract a vector, I simply create a vector that points in the opposite direction as the first one, and that's the vector minus b, and then I add that vector to it. I can also take a vector a and multiply it by a number, like a times this vector a. A might be equal to 6, for example. If I do that, then I'd have to, let's use a smaller amount, let's use 2. Then the vector would be twice as long if that would be a and that would be a. So I've got 2 of these a's, and so this vector here would be 2a. So altogether now, we have 2 operations that we can perform. One is the addition of 2 vectors. The other is the multiplication of a vector by a number. And when we have those and they close, in other words, 2a is still a vector in the space, and a plus b is a vector in the space, and a negative of a vector is in the opposite direction as I just described, so I could have a minus b, then we call this a linear vector space, or a linear vector space abbreviated this way. Linear vector space is a set of objects in several dimensions, and these vectors that form this linear vector space can be added and subtracted, always in giving another vector in the space, and they can be multiplied by a number, both positive and negative. And this gives us what we call the linear vector space. The dimension of a space is the number of numbers that we need to specify a point in the space. So if we think about it, this is a three-dimensional space because we need three numbers. If we needed only two, it'd be two-dimensional. If we needed only one, it'd be one-dimensional. An example of a one-dimensional space is an interstate highway, where the highway markers are sufficient to tell, say, the highway patrol where you're located or where you need assistance. Mile marker 47. And so there, when we have one dimension, we only need one number. On the surface of the Earth, we have a two-dimensional space, and that's because we have we can specify any point on the surface of the Earth or a plane by giving longitude and latitude. This would be mile marker. And an example here would be longitude, latitude. But if you're dealing with an airplane or a submarine, which can go in a vertical direction also, then we'd be dealing with a three-dimensional space. And so we need longitude, latitude, and altitude, or, in the case of a submarine, depth. And in fact, we can do all of the space that we know of in the universe by specifying three coordinates or three numbers that give us the position of an object in three dimensions. Well, what about something that's in four dimensions? Well, if we have something in four dimensions, this is typical for an event. For example, if you meet someone for lunch, you're going to give them three numbers for the space. Usually they assume an altitude of 0. So you'll say the corner of this street and this street on the surface of the Earth at a certain time. And so you often hear that time is the fourth dimension, and therefore it is another number that must be specified to specify what is called an event or an occurrence, such as meeting someone for lunch. We'll get to that a lot more when we talk about relativity. Now here we've talked about the graphical method and how we use this graphical method in two dimensions. But if you really want to know the truth, this method is pretty difficult to actually deal with. And it's good for visualization, so you should understand visually how this works and what a negative vector is and what the sum of two vectors is by putting one on the end of the other one, and how we multiply a vector by a number to make it longer. But there's a much superior method, and I want to first maybe mention the IJK method. There are many people that use a method for discussing vectors, which uses three unit vectors, I, J, and K. And in general, I do not recommend that we use those. It's very dated, and it's a very awkward notation. If you imagine three coordinates, in the x direction, there's a vector called the unit vector I, one in the the y direction, which is the unit vector j, and one in the k direction called the unit vector k. And therefore, you could write any vector, such as a, by writing ax times the vector in the x direction, this unit vector, plus another vector ay, the projection in the y direction, times j, plus another vector in the z direction, times the unit vector k. But this is an antiquated method, and it's very difficult to deal with, and it complicates the notation tremendously. So we're not going to use that. We're going to use the method that we first discussed, where we are representing a vector as a set of ordered numbers. Thus, a vector could be said to be a set of ordered numbers, or sometimes a vector is said to be an ordered n-tuple. So from now on, we're going to represent a vector such as A in its component form, which would be A1, A2, A3, or equivalently, AX, AY, AZ. And if it's a larger dimensional space, we'd have other indices here. And likewise, we might talk about a vector, we might represent this vector in the notation A sub I, where I equals 1, 2, and 3. The advantage of this notation is we don't use up our symbols like X, Y, Z, U, V, W, and gosh, what's next? Z, and so forth. Here we just go 1, 2, 3, 4, 5, however large the dimensionality of the space is. And sometimes in mechanics, we need very large dimensional spaces. So we could represent this vector as the set, and sometimes we represent a set as a symbol with two curly brackets around the outside, meaning the set of AI, meaning A1, A2, and A3 in order. We likewise could represent a vector X as the vector X1, X2, X3, and we'll sometimes do that. Or we could represent that as R, the vector R. And of course, we usually don't use R1, R2, and R3, but this would give us a set Xi. So Xi would represent a vector, meaning the set of X1, X2, and X3. And of course, these will have numbers like 6, -2, and 4 that will give us the components of this vector X as we work with it. Now, the first thing that we want to talk about next is now that we've got our notation down and straight, we want to talk about the concept of a vector product, or sometimes called a scale. First of these vector products is a scalar product. A linear vector space with a scalar product is called a metric space. So a linear vector space plus the idea of a scalar product is equal to a metric space. A linear vector space by itself doesn't give you a whole lot of power. You can point to things and so forth, but that's about it. It's the metric space that really gives us our power. And what is the scalar product? The scalar product between two vectors like A and B is written as A dot B. Therefore, it's sometimes called, rather than a scalar product, a dot product. And this dot product is the first component of this times the first component of that, plus the second of this times the second of that, and so forth. So if our two vectors, A is equal to 1, 0, 2, and the second vector B is equal to 3, 1, 1, then our A dot B is written as 1 times 3, which is 3, plus 1 times 0, which is 0, plus 1 times 2, which is 2, and this gives us 5. So the dot product is equal to 5. So the dot product is very easy to take when we're doing things in this manner right here. We simply multiply the components of the two respective vectors together and then add them all up. You'll notice that this always gives us a number. So the dot product of two vectors gives us a number. For the time being, and in this course, we only need vectors in a real space, real numbers, and so the dot products will always be real. But it's possible to have vectors that give numbers in a complex dimensional space. Now that we have that, you can say, well, okay, what good is it? What good is this scalar product? And the answer to that is A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. And now you see why this is powerful, because we can use this to find both length and angle. That's why it's called a metric space, because we have length and angle that we can determine from this metric space. And how do we get the length? Well, first of all, let's look at the length of A. It turns out that if we want the length of A, it's defined as